I think we should start now. So it's my pleasure to invite you all in the sixth lecture of this series. And before we begin the formal talk and introduce the speaker of the day, so I would like to speak a bit about the genesis of this set of lecture. National Academy of Sciences India, or NASI, is the oldest science academy in India and slightly more than 90 years old. And no other than Professor Meghnad Shah established this academy. And since then, for every academy, there is some mandate. The mandate of National Academy of Sciences is science and society, and it tries always to bring science to society and to do science in a way that helps the society. And keeping that in mind, when 75 years of independence celebration started, and from the last year, so we thought of doing some programs which will bring science to society or encourage the weaker sections of the society to do science. And many programs were taken by NASI, and one such program which is specifically taken by a particular chapter of NASI, which has 22 chapters, and we are doing this on behalf of Delhi chapter of the National Academy of Sciences. And Delhi chapter initiated a program to conduct a series of lecture called NASI Women in Science Lecture Series. And the idea was that the lectures will be delivered by the eminent women scientists, and with the purpose to encourage young boys and girls, and especially the girls, to do hardcore science and to show them that there are really examples of doing good science. And the lecture will have kind of slight part on the problems that women scientists face, how to tackle it, and about the science that the speaker has done. So this is the background, and in this series we have already conducted 5 lectures, and today we are going to have the 6th lecture of the series. And without putting a curtain between you and the speaker, I now introduce my colleague Professor Papia Chaudhary to introduce today's speaker. Professor Chaudhary, please.
Am I audible? Okay. So welcome. Am I audible?
Yes.
Okay. So welcome you all, and welcome Dr. Archana Sharma. And we are very happy that you agreed to give a talk in front of this Indian audience. So without wasting any time, let me introduce Dr. Sharma first. Dr. Archana Sharma, a physicist and a senior scientist at Sun Laboratory in Geneva, Switzerland, was involved in the discovery of Higgs boson particle in sun. Dr. Sharma, originally born in Jhansi, Uttar Pradesh, has received her master's in nuclear physics from Banaras Hindu University and PhD in experimental particle physics from Delhi University. She also received her second doctoral degree, DSc, in instrumentation for high energy physics from the University of Geneva. Her involvement at CERN began in 1987 with a fellowship to conduct research in the detector development. Her research focuses on high energy physics, which explores the origin of the known universe and its component parts. Dr. Sharma is best known for her work in gaseous detectors, through which she contributed to the discovery of the Higgs boson. She has worked on the compact muon solenoid, which is known as CMS experiment, in the Large Hadron Collider for developing a new muon system called GEM, gas electron multiplier. She is the co-owner of patent on a family of detectors called THRAC, that is timing and high rate capable devices. She is an IEEE senior. Dr. Sharma has been on the board of honorary adjunct professor in several institutes where she teaches regular courses on gaseous detectors and their applications in high energy physics and in the other fields like medical imaging and diagnostics, astronomy, space, and PEP. Dr. Sharma has mentored around 20 PhD students during her time at CERN, and she is the author and co-author of over 800 publications. She is also runs an NGO called Life Lab Education and Research Foundation, situated in Delhi, with the main objective to create partnership with educational institutes for the benefit of the underprivileged. Today, our topic will be blue sky, mega science research, coronavirus. Why should I care? So without delaying any much time, so I want to welcome Dr. Sharma to give the talk. Thank you.
Thank you very much for the very kind and generous introduction, Professor Chaudhary. And thank you for this invitation, Professor Ghatak and Professor Pathak. I mean, it is my privilege to be people from my country and from all of you who are there, and somehow the world has shrunk and become so small now with the internet that the distances have disappeared, as we were just saying a little while ago. And I will try to demonstrate that the work that I do is not very fancy or anything that is very special. It's really in the realm of possibilities for everybody. And if you permit me, I can share my screen and start the lecture.
Sure,
And,
please continue.
Thank you. Feel free to stop me, ask questions, because this is really the main purpose of this interaction. It's quite, I would say, informal, despite being a formal lecture. Please feel free to write your questions in the chat, and I will try to address them as they come along. So yes, blue sky mega science research, it sounds very big. You know, we are working in mega sciences, big experiments like this, the thing you see behind me on the screen. This is the experiment, the CMS experiment that Professor Chaudhary just mentioned. And what you see on your screen right now also is the experiment where I work. CERN is a laboratory that is situated between the border of Switzerland and some of the largest equipment on the planet are present here and operational. The point is, why should that is the question. Why should I care? Now let's go a little bit on the history. Why do we study physics? Why do we study quantum physics? Why is it that we are driven by curiosity? And that's the wonder about science, that it makes us curious. It tells us on understanding why at all the apple fell from the tree. And although it is a very simple thing, today we can say it's obvious, there must be a force, but it was not obvious until somebody was curious about it. And I'm sure that, of course, everybody in the audience knows Newton and Albert Einstein, who gave us the theory of relativity, so that the dream to understand the microscopic to the macroscopic to the extra galactic scale of matter could be understood. We could understand what are the fundamental building blocks of matter, how they interact amongst each other, and how at all did the universe come about. So these are the questions and very ambitious goals that scientists and physicists have put in front of them. And I'm pretty sure that in the audience, there are people like me who, when we were always had these kind of questions. How did the universe begin? Where did we come from? And of course, it's not sure that we have the answers, but we try to find answers when we look at experiments that are happening in astronomy, in astrophysics, who are looking outwards with telescopes on a scale that is very large compared to what we do here, experiments at CERN, where we look inside matter. We try to recreate the Big Bang that is supposed to have resulted using the simple formula E is equal to mc squared, that has resulted in the universe as we know it today, and how will it evolve? Those are the questions which we also need to answer. So the Large Hadron Collider is an accelerator. I will come to that in a bit, but just to say that this experiment that we have here at CERN is based on an accelerator which smashes particles to reproduce the conditions at the time of the Big Bang. So we look inside matter at the microscope with the accelerators, and then we try to understand what has happened in the 13.8 billion years when we come to today. And of course, we can study these particles that were present at the time of the Big Bang. So yes, science, physics, methodologies, experiments, astronomy, cosmology, all things come together when we try to understand what is matter and how does it interact with each other. This is something which is extremely, let's say, puzzling to us. But nevertheless, if I give you a marble, you know, kancha, which kids play sometimes, if I ask you, what is it made of? You will try to look inside it or shine a light across it and try to see what is it made of. Or else you will try to shine some kind of, another kind of light like radiation, and then try to see a shadow of what is inside this marble. Or you will break it, then try to see what is inside it. And there was one such physicist called Bibha Chaudhary in our country, who in the 1940s started making detectors that would study showers in cosmic rays. And she built detectors that some of them are still in the Tata Institute of Fundamental Research, where she made these wonderful pictures, and these pictures have been published in the journal Nature. So you can imagine that creativity can be coming from any corner. And in our country, we have had stalwarts. We are standing on the shoulders of scientists who have shown us the way. There has been Satyendranath Bose, Bhabha, Meghnad Saha was already mentioned. So of course, this is not a lecture about the history of physics in India, but I wanted to highlight that women in Indian science have been there from a very long time. The only thing is that we need to their achievements. Having a publication in Nature is not something very simple. And making a detector in those days when theoretical physics was more the norm, even today, in fact, is something which is still, let's say, it needs a lot of development to come at par with where we could be with a little more effort. So yes, we need to look at the technological advances in instrumentation. Professor Chaudhary had mentioned my second degree. My second degree, PhD degree, was a DSc, in fact, from the University of Geneva. So why did I do it? And I need to just admit here that when I arrived in Geneva in 1987, it was impossible for me to be working in an electronics where I had never, ever seen the simplest of instruments in Delhi University or in Varanasi, where I studied for my master's and my PhD. So these are just pictures to show you that really I am one of you, one of the students that you are teaching, or one of the students who is in the audience. And on the top left, pictures from my school, my college. And of course, this is St. Francis Convent High School, Jhansi, it used to be when I was studying there. I went there later to take this picture, of course. And on the very right-hand bottom, you see me struggling with electronics when I arrived in Geneva for the first time in an electronics laboratory where detectors were being designed and tested and so on. But again, I think rigor, persistence is really the key. And we do not take defeat, right? So we need to just continue on that. And I have been working now on many, many projects, and I'm leading also several projects. I'm working CERN-wide, leading big projects like, you know, the mitigation of greenhouse gases, or I'm working on the international relations with organizations like the United Nations and WHO and so on. And of course, on the right-hand side top, you see the detector that I have installed in the CMS experiment only in the last couple of years. So the journey has been long, difficult, challenging, but it's not impossible. In the middle somewhere, you see me with a colleague with a detector that is shining this copper kind of color. That's the detector for which we have the patents, and they were invented in the laboratory while we were working there. All right, so I've been working on R&D, building and commissioning detectors for a long time. And of course, at CERN, as we mentioned, we are looking at the questions about the universe. There are many, many open questions, which I guess that the audience must have in their minds, and maybe some of you are physics students, so you try to imagine what is the origin of mass, what is the nature of dark matter, why do we call it dark? Simply because we do not understand it. And of course, why at all is matter there? We know from all the measurements of the cosmologists and all the studies that and the beautiful pictures that you have seen these days floating around over the last, let's say, 5 years since gravitational waves were discovered, that whatever exists out there is all matter. Where has all the antimatter disappeared? So when the Big Bang happened, because of symmetry, matter and antimatter formed in equal proportions. But there is an asymmetry because we exist. And all of us are made out of similar protons and neutrons, not similar, identical protons and neutrons. So what exactly happened at the time of the Big Bang? So to answer these questions, we have opportunities which we study in the theoretical and experimental nuclear and particle physics. And today it's also called high energy physics. So we unlock the secrets of the universe, and you all can be connected with it. Your students can be connected. Your younger students in high school can also be connected, because there are challenges and opportunities for everybody. What you see on the left is the present accelerator, the 27 kilometers circumference of this accelerator. We will get into more detail later. But this is the largest equipment on the planet. And we have several experiments that are running on this accelerator. It took about 20 years for designing and building it, and then commissioning. It started running in 2010. And when this research was happening, rather when it was proposed and approved, at that moment of time, people did not know what are the kinds of technologies that would be used to build it. So that's called cutting edge technology. Work together with industry to develop materials, to develop semiconductors, to develop superconducting magnets, which can go up to fields so they can accelerate the protons to go to the speed of light. So all these things have a spin-off directly into society. The picture you see in the middle is the application of these accelerators for cancer. And in the world today, we have more than 30,000 accelerators, and more than half of them are in hospital. So yes, there is a very compelling need to engage with fundamental research, because this is a driver of innovation. And it's through basic research that we are able to unlock the potential for wide social impact. I mean, if J.J. Thomson had not discovered the electron, we would not have been looking at our mobile phones every 10 minutes, right? Or if CERN had not invented the WWW, we would not be so empowered today that we couldn't imagine a life without the internet. I mean, children, millennials, they could not imagine that we had to wait sometimes even months to get a reply to a publication, whether it was accepted or not. So yes, these are important social dividends that we can get when we invest into international collaborations for fundamental research. So yes, current understanding of matter, I think everybody in the audience knows the picture from the left to the right. Let's go directly to the quarks and the leptons, which means that we are inside the atomic nucleus, and we are looking at the hadrons, which means protons and neutrons that can feel the strong force. And these protons, they are made out of quarks. And if we want to move the quarks away from each other, they just do not they do not go away. The force becomes stronger and stronger. So that's the source. And of course, the electrons are the known leptons that we know. But how do we know this? It's exactly what we had been doing with the marbles when I gave you the example, which means that we smash things together and then we try to look inside. And doing that, many experiments have been performed, many particles have been discovered, and the physicists also have their own periodic table lists. And this is called the standard model of particle physics. Very nicely, the ordinary matter belongs to one group called the leptons and quarks, electrons and the electron neutrino, and up and down quarks. But then we have discovered these other particles, and they also fit very nicely in the standard model, and they are heavier cousins of the first group, so to speak. The muon neutrino, the charm and the strange quarks, the tau neutrino, and the tau particle, and the top and bottom quarks as well. And in addition, there are antiparticles also that fit on this. And now let's see how at all can we make such an experiment where we can look inside matter. So imagine two helicopters made out of Lego, and when we smash them together with some energy, they break down. But as you see on your screen, the collision energy is not enough to go into the fundamental particles. So let's try to go further and see. It's going a bit slow, but because there is not enough energy, I hope that this will be faster for the next one. So yes, we got pieces, and we know that these are not fundamental particles. We increase the energy, and they break down again when we increase the energy, and we smash these two helicopters, imagining that they are made out of Lego pieces. And these Lego pieces, the energy was sufficient to break down into fundamental particles, right? So physicists have been doing these kind of experiments where they are smashing particles that are composite, like the protons. And when they smash together, we are able to identify the structure of matter. And of course, physicists like to be very elegant with mathematics also. And of course, we have those of us who have studied quantum mechanics and the theory of relativity and so on, we know that the world can be nicely described by this beautiful equation you saw on the cup. But now I'm doing another experiment. What happened here now? We still had our helicopters, but then what did we increase? We increased the energy. And when we increased the energy, what happened? We did not get the fundamental particles. We got something else. And this something else means that the energy that we gave to the particles, it created mass, which was different from what we started. So we got something like dinosaurs, and they existed at the time of the Big Bang, so to speak. I mean, of course, you see it's an analogy. And we can recreate, when we do this kind of experiments, we can recreate particles existing at the time of the Big Bang. So we start with mosquitoes like our protons, but we get lots of other things when we do these experiments. And some of you may have heard about the Higgs boson, boson with a big B, because you know Satyendranath Bose was the one who had proposed how the bosons should behave. So we really owe a lot of the science that we study and the behavior of the particles that we study to the scientists in India. So now let's move on. We have done our accelerators. These are powerful machines. They are accelerating the particles to very, very high energies, close to the speed of light, 0.999999 times that of the speed of light, so that the equation that you know very well to mc squared happens, and we get new particles. Now, how do we study these particles? We have to take pictures of the collisions, right? But these collisions must happen at a very high rate so that improbable interactions can also take place, and we are able to detect particles that have a very small probability. And those cameras, so to speak, are called giant detectors. We need computing, of course, because without computing, we are not able to collect and store this data, which is a huge amount of data. And parenthesis, everybody can access data and everybody can do this analysis back home, sitting at home. One day I was called by the press office at CERN and they said, Archana, do you know that somebody in Kerala has got a prize for working with the LHC data? And it was just incredible that it was a high school student who had taken access to LHC data and just volunteered his computing resources that he had to be used in the grid computing, So just by doing that, he actually managed to be a part of the whole experiment. So yes, being collaborative is extremely important. And we need not only students, scientists, engineers, technicians, but we need a huge amount of support staff also to design, build, and operate these complex machines. So as I mentioned earlier, 27 kilometers of two pipes. It means 54 kilometers of the largest microscope on the planet, right? And you see on the left, two beam pipes. This is just a cross section, which have a vacuum, which is the tightest vacuum on the planet also. And collisions happen on different points of this circumference of the accelerator. This is 100 meters underground, by the way. And wherever the collisions happen, we have experiments. And these experiments are also located underground. What you see in this picture, on the top are the Alps, the mountains in Switzerland and in France. And the lake, you see the beautiful lake also. But experiments are underground, and we go down to actually observe these collisions, take data, and these are our beautiful. Behind me also, you see that experiment, and you see a picture on the screen also now. This is the experiment called CMS. It has taken nearly 15 years for designing and building together. And it is indeed an experience where even just by the fact of being in the experiment, interacting with people, you are able to just gain and learn. So imagine if a fish is thrown in the ocean, will die, or she will learn how to swim a size which is never possible in an aquarium. So this is the kind of challenges that we face. And here we have these experiments which are dedicated to particular physics questions. For example, as I mentioned earlier, the quark-gluon plasma at the primordial time of the Big Bang, or to look for the Higgs boson. And these are multi-purpose experiments, ATLAS and CMS, so that you can look for supersymmetry. I will not go in any technical detail, but just to say that surprises can be looked for in these experiments. And the LHCb experiment is looking at the matter-antimatter asymmetry. So I do have actually large number of slides of only women at CERN in India who are working on the different parts of these experiments, but it would take another lecture only to go through the contributions that are going on with all these women in India. I just flash a few here and there. And these are people who are working in India, in Chandigarh, in Jammu, in Jaipur, in Kolkata, who are building detectors in India, bringing them to CERN, installing them, taking data, and then, of course, doing their PhDs and, participating in these different kinds of physics endeavors, of course. So the Higgs hunters, as they are called, as I had mentioned a moment ago, the ATLAS experiment is a very big experiment. If you see on the left, you see a tiny figure of a person also. And now it tells you the size of this experiment, which is 70 meters long and 40 meters high. CMS on the right-hand side is a compact muon solenoid. Although it is compact, it is 14,000 tons, 14,500 tons, in fact. And the overall diameter is 15 meters and length, actually right now it is 40 meters, not what is written here because it has grown ever since this picture was made. So yes, this can only happen when we work together, and no one person or one country or one region actually do these kind of experiments. We have all to come together, and everyone needs to really engage and exploit the power of collaboration and see more examples of my fantastic girl scientists and women scientists, not only working at the for engineering or for the physics, for example, but they're also working in science communication. So yes, there is amazing example. You can see my slides at length later on, because I have explained also here what they are doing and how they are contributing in the experiment. And there's a girl called Archana Sharma as well. We call her Archie, just so that we are not confusing each other, but we do still get confused. But just to say, so many role models are in front of you. They are coming from all corners of India, and everybody is doing amazing work as far as the CMS experiment is concerned. And of course, on now you see a real collision. So we have collisions 40 million times in 1 second. So imagine taking pictures of the collisions 40 million times in 1 second. And why do we have to do that? Because we need a huge amount of data sample, so that one Higgs or one rare event or one exotic decay can be spotted out of 10 to the 14, 10 to the 15 events, right? And it was actually possible. In the summer of 2012, the Higgs boson that was postulated in 1964 was actually observed at CERN by both experiments, ATLAS and CMS. So this was a fantastic day where there was a seminar that was given all over the world on the 4th of July, 2012. And the following year, the Nobel Prize went to Professor Francois Englert and Peter Higgs, who had theoretically explained the mechanism by which subatomic particles get mass. And this discovery of the fundamental particle was done by the ATLAS and CMS experiments at the Large Hadron Collider at CERN. And we are all part of it. We are very proud part of it, as you can imagine, because if we were not, we would not be moving ahead. And I'm sure you see many smiling faces in front of you. And these smiling faces are all people who are working day and night from years on end to make sure that these kind of successes can be repeated and brought more and more in the Indian context. Because at the moment, it is clear that no one country can do it. However, India is 1.3 billion people. We need 2% to actually make such a, we can be driving what we are doing in terms of not only particle physics, but the social impact. We can pick up technologies and relate them to medical applications, for example, and then have a facility in our country. And I would be so delighted to see some of you come together and we work together on such a kind of facility. So just to show that another girl, she is very young, of course, and she was appointed in 2021 as member of the new Mega Science Vision Group, because in India we have the STIP process just happened. The Science Technology Innovation process happened in 2020. And after that, the Mega Science Vision 2035 is being articulated, and Bhavna is part of that group. So yes, Higgs boson की खोज हो गई. अब हम क्या करें इसके बारे में? बहुत अच्छी बात है कि फिजिसिस्ट इतने खुश हैं, लेकिन हमें तो कुछ करना चाहिए ना. Why should I care about it, right? अब आप सोचिए कि आप जब हॉस्पिटल जाते हैं और आपकी एक बोन टूटी है, तो आपको क्या करना पड़ेगा? एक एक्सरे लेनी पड़ेगी कि नहीं? लेकिन जब एक्सरे हम लेंगे, जब अगर हमारे पास एक्सरे नहीं होती, किसी ना किसी ने, तो there was some physicist in the laboratory who discovered how we could use X-rays to look inside the human body, right? Similarly, quantum mechanics पढ़ के हमको पता चला कि हम इलेक्ट्रॉन माइक्रोस्कोप बना सकते हैं. And with the scanning transmission electron microscopes, we can get a resolution which is 200 times better than in the normal annular dark field imaging mode. So magnifications आप सोचिए कि कितना हम देख सकते हैं. And that is how COVID-19 का जो first selfie मिला था, that was only possible because electrons were discovered. Quantum mechanics was known. Electron microscope बना था. So the first 3D map of the coronavirus protein opened the door to a vaccine. और यदि हम तैयार नहीं होते, हमारा इंफ्रास्ट्रक्चर तैयार नहीं होता, तो हम किस प्रकार वैक्सीन और ये जो अमेजिंग चैलेंज को इंडिया ने डेमोन्स्ट्रेट किया है वर्ल्ड को कि हाउ वी हैव बीन एबल टू क्रिएट द वैक्सीन्स and get the whole population vaccinated with a portal on the web. All this was impossible without the power of technology, science, and innovation. So I would like to highlight here that there is no wall between physics, chemistry, biology, software. Everything has to come together. आज के ज़माने में जिस तरह से the planet has come together, any problem is our problem, whether it's climate, whether it's meteorology, whether it's pollution, whether it's climate change. So all that is something that we should think about and how we can come together. And being a particle physicist is a training that you get when you have a creative period. You build prototypes, you think about how to make a sensor. मैं radiation को कैसे use करूं to be able to look inside something or to make sense of the data that's coming out. आज we are using the WWW for financial institutions, trillions of dollars of financial management is happening through the WWW. So जब WWW बना था तब तो किसी था कि ये हम किस तरह से यूज करेंगे, but today we find it impossible कि how the world will communicate if there were no mobile or you see what I mean, that when you are engaged in research, you become so creative that you are able to then take that research and apply to many different fields. Okay, काफी कंफ्यूजन हो गया, आई कैन इमेजिन, क्योंकि ये तो बहुत बड़े बड़े एक्सपेरिमेंट्स हैं, बहुत बड़ी थ्योरी है, बहुत बड़ा बड़ा चैलेंजेस है, और ये बहुत इजी है कंफ्यूज होना. मैं भी इसी तरह से कंफ्यूज रही हूँ अपने जीवन में और अपने करियर में, बिकॉज इतना जार्गन है, उसको समझने में भी टाइम लगता है. तो उसके लिए परेशान होने की कोई जरूरत नहीं है. स्पेशली आई एम स्पीकिंग टू द यंगर पीपल हियर. यू जस्ट हैव टू इमेजिन कि कुछ भी इम्पॉसिबल नहीं है. एंड वंस यू कैन इमेजिन कि कोई भी आपको कुछ भी बोले, बिकॉज द फर्स्ट थिंग पीपल टेल यू इज अरे ये नहीं हो सकता. This is how things happen. Even if it starts from home, your parents will tell you sometimes, "Yare, ye to nahi ho sakta." But then if you are convinced, if you know that this can happen and that you would absolutely to go in that direction, it can take time, but it can happen. So after about 20 years at CERN, I had a dream in 2009 that जो मैंने R&D किया था 90s about a detector that was mentioned before by Professor Chaudhary, the GEM, the gas electron multiplier detector. उसके ऊपर मैंने R&D किया था 90s में, और मैंने ऐसे कभी नहीं सोचा था कि मैं इसके साथ में आगे क्या करूंगी. But I managed to write down the dream with the help of a team that we put together, and this dream was then realized 10 years later. ये फोटो आप जो देख रहे हैं, ये 2020 की फोटो है, where we had installed the last gem detector in CMS, and it was such a roaring success that we were so happy packing up these detectors जहां लैब में बन रही हैं ये. Of course, long story about how they were done and how they have been coming together from 17 different countries on the planet. And उसके बाद हमने जब install किया, we also got a little prize on that. And you can see how many girls there are here right in front of you who have been part of this dream and also part of the implementation. So you can see here that this is how it was installed. और ये बिल्कुल last वाला detector was being installed in CMS, right? So yes, big science wins many prizes, And हम लोग सिर्फ प्राइज के लिए काम नहीं करते हैं. So I would now like to show you a little small film about India and the scientific excellence that we have in India. ये सब स्टूडेंट्स हैं इंडिया में. इनफैक्ट दिस वाज अ सेमिनार इन मिरांडा हाउस इन यूनिवर्सिटी ऑफ दिल्ली. This book is available for free, by the way, and it will push you कि आप कहाँ अपने आप को जोड़ सकते हैं इस मिशन के साथ, right? Everybody, कहीं भी हो, आप बुलंदशहर में बैठे हो या फिर आप कोलकाता में हो या फिर आप कहीं हैदराबाद के किसी को या कहीं पर हो, that's the work that the foundation has been doing. So I wanted to show you just a couple of more things. One is about, you know, the medical applications. Just imagine, अभी तो हम एक्सरे की बात कर रहे थे. Now you can imagine कि अगर हम वो एक्सरे को कलर में देखें, because of the contrast of the muscles and the tissues and the bones, that's the picture that you're seeing on the screen. जो ये आप घड़ी के साथ देख रहे हैं एक picture, that is a picture that has been taken by one of the detectors जो हम use करते हैं अपने experiments में, and the same detector has been used then for the imaging of the wrist of one of our scientists. So बहुत इसमें वो है. I'll just show you maybe one picture on the bottom right. Now you can see कि किस तरह से you can see 3D slices, and it is a doctor's delight to see through the body without any invasive therapy or बिना काट पीट के they can see inside the body, right? So अच्छा, this I have already shown, so I should just go through again. So yes, I hope that I have convinced you that curiosity about the universe will impact. How? क्योंकि हम answers ढूंढ रहे हैं. For the answers, we are looking at technologies, innovations, and in every direction. Not just in, like, you know, we don't imagine that this is particle physics, तो वो एक डिब्बे के अंदर बंद है. It's not like that. It's really all about the society. It's about sustained development goals. And we have the beautiful picture of the table laid out by United Nations about the sustained development goals. Or every one of us, each one of us has the opportunity कि हम किस तरह से अपने को align करें sustained development goals के साथ, plus with national priorities. What are the priorities in our country? And I don't have to tell you about that, right? So उसको देखते हुए, we have been interacting with a large number of scientists in India. And by we, I mean myself and one of my colleagues, Purti Raman. She is a science communicator, and this is what we came out with. Okay, so that's what was the book about, and I think with that I will close my my lecture here, and I will just repeat that opportunities are for everyone. You just have to think and think and think about them. How can I engage? And the best for every one of us is around the corner. I wish everyone all the best. Thank you.
It was wonderful and extremely encouraging. And now it's open for question, and we'll appreciate primarily question from students. So student, you can raise hand or you just can unmute yourself and put your question. You can ask anything that comes in mind, means you don't think that this question will be silly or not. Anything that comes in your mind, you can ask.
Okay, so maybe I can start by telling you that when I came here to CERN, the first thing I had to overcome was to ask a question. Because I used to be so shy that in the meetings, even if I knew the answer, I was not confident that the answer is correct, you know. And I used to really kick myself when other people used to give the same answer that I had in my mind, but I was not able to say. So I think the best way to learn is by being corrected. So there is no harm if you ask a question, and if it is not a good question, there is first of all no question that is a bad question or a silly question or a stupid question. The question that is the stupid question is the one that you did not ask. So come on now, let's hear from you. And I would like to hear from some girls here. I see many of them joining here. So please, बिल्कुल आप आगे आइए, बात और यही मौका है, ठीक है ना? तो दो बुक्स के बारे में आपसे बात हुई है, बुक्स देखिएगा. वन इज अवेलेबल फॉर फ्री, दूसरी वाली भी बहुत अफोर्डेबल है. इट्स 350 रुपीज की है दूसरी वाली बुक. वो पब्लिशर माने नहीं उसको फ्री कर, वो दूसरी वाली भी फ्री करते हैं हम. सो क्वेश्चंस कोई
हेलो
तो. यस यस लवी.
मैम, आपने मैम जो अभी एक्सरे का एक वो रिप्लेसमेंट बताया ना मैम, ब्रेस्ट का जो आपने दिखाया है स्लाइड बाय स्लाइड, तो एक्सरे तो जैसे हार्मफुल होता है, तो वो रिप्लेसमेंट भी क्या, मतलब क्या वो हार्मफुल नहीं है बॉडी के लिए, या वो ज्यादा हार्मफुल?
वेरी ब्रिलियंट क्वेश्चन आई मस्ट से, क्योंकि दिस इज प्रिसाइजली द पॉइंट. क्योंकि जब आप एक्सरे करने जाते हैं तो आपने देखा कि टेक्नीशियन या तो खुद वो लेड का एप्रिन पहन लेंगे, या तो वो कमरे से ही बाहर चले जाएंगे. वो सिर्फ पेशेंट बैठा होगा अंदर, एंड पेशेंट इज द वन हु गेट्स द डोज. लेकिन जो ये वेरी फाइन डिटेक्टर्स हैं with the materials that we are using now, with the algorithms and smart algorithms that we are using now, 200 times less dose is given to the human body. So I would encourage you to study Mars bioimaging. यहाँ तो देखिए कितनी तेज चलती हैं चीजें कि लैब में ये हुआ और एक कंपनी ने बना लिया, you know, and it is already commercialized. So अगर कोई इंडिया में करना चाहता है इस तरह के काम, so please come forward and we will try a detector made out of gems for medical imaging. ठीक है ना? That project is waiting to be done.
What about the size of these detectors you are mentioning?
जी 40 सेंटीमीटर है मेरे ख्याल से. तो 40 सेंटीमीटर एवरेज जरूरत होती है, 40 सेंटीमीटर स्क्वायर. So that is the size.
And cost?
अब कॉस्ट का तो डिस्कशन
in comparison with X-ray, which we have in every pathological lab nowadays, here and there. So
of course it will take time for the cost to come down, that is clear. आप कंपटीशन करेंगे ना, देखिए अभी तो मार्स बायो इमेजिंग ने बना लिया है एक और अपना बेचेंगे वो लोग. लेकिन अगर हम इंडिया में अपना नॉट जुगाड़ बट बेटर देन जुगाड़ कुछ कर लें तो बी एबल टू मे बी सेल इट चीपर, है ना? Yeah.
Next question, please.
You know, I'm a very naughty teacher. मैं फिर नाम लेना शुरू कर देती हूँ कि भाई आपको पूछना पड़ेगा. So you have to come up with your own question जल्दी से.
Ma'am, can you explain once again the thing when why we need million times collision in a second?
जी.
That portion.
ओके सो आप ऐसे सोचिए कि आपके पास ना एक बहुत बड़ा खेत है, ठीक है? खेत, यू अंडरस्टैंड, है ना?
Yes.
तो खेत भरा हुआ है, जमीन में तो धूल भरी हुई है और ऊपर तक जहां तक आप देख सकते हो वहां तक उसमें घास भरी है, ठीक है? एंड इट्स अ वेरी वेरी बिग खेत. उसमें एक आपको सुई ढूंढना है, ठीक है? तो आप क्या करेंगे? आप एक चम्मच से तो ढूंढेंगे नहीं, ठीक है ना? कि चम्मच, एक चम्मच घास उठाएंगे, उसको फेंकेंगे, उसमें सुई है नहीं फेंकेंगे. सो सिमिलरली जो थियोरेटिकल कैलकुलेशंस होते हैं उनसे हमको पता चलता है कि जो इंटरेस्टिंग फिजिक्स पार्टिकल्स हम ढूंढ रहे हैं, जो नोन है और जो अननोन भी है, वो उनका जो क्रॉस सेक्शन होता है. क्रॉस सेक्शन यानी कि अगर हमारे पास 10 to the power 14 collisions हम कर रहे हैं, उसमें जाके हमें एक शायद मिल सकता है, that is the probability. तो इसलिए हमें बहुत डेटा, तो बहुत डेटा का मतलब है कि हम जब हमारे पास बहुत डेटा होगा, the probability of finding the Higgs or these any processes increases. और उसी वजह से हमको Higgs 2012 में मिल पाया, because एक collision, we have collisions that are 40 million times in 1 second and we are running for 6 months. तो आप सोचिए कि क्या कलेक्ट कर रहे हैं. We are talking of petabytes of data. One event is 200 GB. Sorry, one event is 200 gigabytes, yes. और 40 मिलियन एक बार में हो रहे हैं, तो उसको कैसे हम सॉर्ट करते हैं. उसमें से मोस्टली तो हमको फेंकना, मोस्ट ऑफ इट इज गार्बेज. जैसे खेत में मैंने बताया ना कि मोस्ट ऑफ इट तो घास फूस ही है, उसमें हमको जो इंटरेस्टिंग मिलेगा ना, क्योंकि जो हमारे फर्स्ट वो होंगे, क्या बोलते हैं, जो फर्स्ट एल्गोरिथम्स होंगे वो तो यही होंगे ना कि अब पता नहीं मिल रही कि नहीं मिल रही, लेकिन इज द वेट ऑफ दिस अमाउंट ऑफ घास more than the average of घास, मतलब कि yes there is some signature, something can be there. तो ये interesting event है, चलो इसको रख लेते हैं, बाकी को फेंक देते हैं. So you know there is a trigger system that works. So I hope I have explained कि why you need a huge amount of data.
Thank you.
Who is asking the next question? Please just unmute yourself and ask whatever comes in your mind.
Ma'am, I have a question.
Banipreet, continue.
Yes, yes. आपको अनम्यूट करना पड़ेगा. You are muted, Banipreet.
Oh, sorry, ma'am.
Hey, ma'am.
Actually, I was asking that there are portable X-ray machines available nowadays. Like people come to our house to get, we can get our X-rays at home. So, ma'am, how is it possible? Like, won't they miss? Like, I don't think, according to me, it won't be that efficient. So, how does that work?
What will not be efficient? X-ray machine को लेके जाना इधर से उधर?
Yes, ma'am. मतलब उसके रिजल्ट्स इतने एक्यूरेट नहीं होंगे, ऐसा मतलब हो सकता है.
You are talking of the new machine या portable machine? Are you talking of that
Yes,
machine?
yes,
Okay.
ma'am. Portable machines.
नहीं, nowadays you know, आप कैमरे से, आईफोन कैमरा से,
No, ma'am. Actually, not
no,
through.
I'm just asking you that you are taking your photos with iPhone camera wherever you go, or any other Samsung or whatever. I don't mean to take any name of a brand, but आप अपने कैमरे से फोटो लेते हैं, कहीं भी जाते हैं, correct?
Yes,
So
ma'am.
it means it is a portable camera. पहले हम लोग स्टूडियो में जाते थे अपनी एक पोर्ट्रेट फोटो खिंचाने के लिए, राइट? लेकिन अभी हम फोटो कहीं भी ले लेते हैं. एवरीबडी इज अ फोटोग्राफर, एवरीबडी कैन मेक अ मूवी, एवरीबडी कैन डू थिंग्स. सो टेक्नोलॉजीज हैव गॉन अप बाय सो मच दैट मोबाइल, it is like taking a photograph with some radiation, जैसे एक्स-रेज होती हैं उसी तरह से. और now we have huge amount of monitoring, safety, algorithms that and materials that protect the X-rays from coming out from wherever it is. आपको authorization नहीं मिलेगा मशीन को यूज करने के लिए if it is not fit for using for a human being. You see, that's why we have ICMR in India. ICMR है ना इंडिया में, Indian Council of Medical Research. उनसे आपको पहले एक सर्टिफिकेशन लेके आना पड़ेगा before you can use any machine in the hospital or it for medical purposes. ठीक है ना?
Okay, ma'am. Thank you, ma'am.
या लेड का बॉक्स के अंदर रखना पड़ेगा, लेड की थिकनेस कितनी होगी ये कैलकुलेशन करना पड़ेगा, एंड देन यू गेट योर अप्रूवल्स.
Any other question?
I think people are shy.
Yes, means
कोई बात नहीं, you can later also.
हेलो मैम.
Lavi again, please continue.
मैम मैं पूछा था जो हेलो
जी
मैम, मैम ये जो मार्स बायो इमेजिंग की फ्रीक्वेंसी रेंज होती है वो क्या होती है मैम? जैसे
अब ये तो देखना
एक्सरे
पड़ेगा
10 to the
जी।
power 16 to 20 जाता है एक्सरे। अच्छा
You have to see what kind of radioactive source are they using. अगर strontium use कर रहे हैं तो strontium की lines होंगी उसमें, और rubidium use कर रहे हैं तो उसकी होगी। अब ये मेरे को exactly नहीं मालूम है, but अभी ख्याल नहीं है मुझे। But you can take a look. That's why I wrote it in the chat. So you Google them up and you'll get everything. Google Baba has all the information.
So is there any other question? If not, we would like to thank the speaker on behalf of the National Academy of Sciences India as well as JP Institute of Information Technology. And I would also like to thank everyone present here for a patient hearing and getting engaged in the discussion, and those who did not ask questions but had questions in mind, they may drop questions by mail and I can forward the mail to if you are interested, and or if some questions come later on when you think about the talk, about the universe, about the particle accelerator, about the fundamental particles, anything that comes in your mind, you can drop me a mail and I can forward your mail. So we'll continue with this series, and the next lecture will be on the 3rd week of September, and we'll share the notice soon. So till then, goodbye, and once again, thank you everybody for joining in this lecture.
Thank you, Professor
Thank you.
Pathak, and thank you, Professor
Thank
Chaudhary.
you.
Goodbye. Bye-bye.
Bye bye. Bye bye.